Welcome back. In the last lecture, we looked at a competition model for two species in the same ecological niche, the competitive Lotka-Volterra model. In this lecture, we'll look at another competition model for two species, but in this case, one eats the other, and this is called the Lotka-Volterra predator-prey model, and we'll also discuss some other models. So first we'll begin with a predator-prey introduction. Then we'll look at the Lotka-Volterra model, and then we'll discuss some of the mathematics and graphing, and then we'll simulate the system in Python. So predator and prey populations cycle. And in this example, with hares and lynx in northern Canada, the hare population increases first, which is the blue line. For example, the lynx population is low in 1848 through 1850. And then the hare population jumps up because there's a low predator pressure. And then the lynx population doesn't increase immediately, either due to slow reproduction or other factors. But once it does catch up, then it starts to decrease the hare population. And so these cycles happen over and over. In this case, it's in decades. And actually, we've been looking at this part of the curve where there isn't such a close correlation between hare and lynx populations. But you can see that beginning around 1900, there is a closer correlation between hare and lynx populations. And I don't know why the correlation is lower here, whether it's sampling or some other factors involved. This was actually compiled by the Hudson's Bay Company in northern Canada. And actually, the lynx population is measured in thousands of furs that they collect per year. And I don't know how they measured the hare population. Obviously, there wouldn't be a one-to-one correspondence between lynx and hares. But anyway, you can see the cycles in this case. So before we looked at the competitive Lotka-Volterra equation, where we had two populations competing for the same prey, for instance, lions and hyenas. So this was the equation we used before, and this is not the equation that we're going to use in this lecture. So the traditional predators and prey in the Lotka-Volterra equation, which was developed in the 1920s, were owls and voles, where voles are a rodent and the owls are the predator. And notice that there's no carrying capacity in this equation. And the assumption is that the interaction between the two controls the population and the environmental carrying capacity is much higher. So there's four components to the equation. There's the growth or reproduction rate of voles, alpha V, where R is like the exponential growth coefficient, or alpha is like the exponential growth coefficient R that we've been dealing with before. And so this is exponential growth because we're far away from the carrying capacity. The second term is the death rate of owls. And this is just the normal death rate. So it would be the 1 over the lifespan of owls. Then we have the gamma VO. So this is the interaction of voles and owls, and this is the rate at which owls kill voles. So this is dV over dt equals gamma VO. And then we have the growth rate of owls as a function of owls and voles interaction, with epsilon being the growth rate term due to that population or that interaction. So what we can do is we can determine the nullclines, and in order to evaluate the nullclines, we factor out the V and O in the equations. So remember, for a differential equation, this V for dV over dt is the trivial result, So this is the result that determines the null line inside of the parentheses. And so you can see that if dv over dt equals 0, then we set alpha minus gamma O equal to 0. And so O for the dv over dt null line is alpha over gamma. Likewise, for the do over dt null line, so no equals 0, so no change in L's at the null line. We have vols equals delta over epsilon. So here are the null lines. And remember, in the competitive Lotka-Volterra equations, the null lines parallel each other, but in this case, they're perpendicular. So the null line for owls is the vertical line at delta over epsilon. So this was the voles population at which there's no change in owls. And the reason you know there's no change in owls on this graph is that the population growth vector is horizontal and owls would be increasing up or down. So there's no change in owls here with voles. Likewise, there's no change in owls here with increase in voles. And we increase in voles if the owls have a low population, and we decrease in voles if the owls have a high population. So this is the null line for voles. So you can see that the population growth vector is vertical, which means there's no change in this direction for voles. And if the voles have a high population, then the owls increase in population. And if the voles have a low population, then the owls decrease in population. This point here is the equilibrium point where the null lines cross. So for example, we're going to have an example where just a really simple example where we set all the terms epsilon, gamma equal to 1, and then 1, 1 is going to be our equilibrium point. So if we start the population at voles equals 1, owls equals 1, we're not going to have any change. So we're going to see that in our example. Okay, so there's stable and unstable scenarios. And so if we plot one species versus the other, then as you might have noticed in this graph, you can see that the population cycles like this. And so in this case, this is unstable, which means the fluctuations increase. They become greater. This is the stable case where the population fluctuations decrease and they gradually dampen out to the equilibrium point. And this is also called stable, where there's no increase or decrease in fluctuations. So this is our in-class exercise here. I'd like you to set up the Python code for the following parameters. I'd like you to put the owls and voles differential equations into the Euler model. So remember, you have v at n minus 1, or v at n equals v at n minus 1 plus v at n minus 1 times alpha, and then here we have O at n minus 1. And we have to multiply that times dt. So you have the original population plus the change times dt. Similarly with the owls population. So you'll have two equations in your for loop, one for owls and one for voles. I'd like you to initially set all the coefficients equal to delta equal to 1. And I'd like you to initially set the V and O populations equal to 1. And I'd like you to then plot V and O versus time. And you should just see a horizontal line because they're starting at the equilibrium point and they'll remain at the equilibrium point. Then I'd like you to set the initial V equal to 2 and O equal to 0.5. And I'd like you to make the state space diagram, the change over time, and observe the long period behavior. And what you're going to have to do is you're going to have to set your time steps low in order to have a steady state, which is what you'll have. And steady state doesn't mean no fluctuations. It just means the fluctuations aren't going to increase over time. So that's called stable. And I'd like you to plot V versus O. And I'd also like you, if you can, to observe the direction of the cycle. Okay, go ahead and stop the video and work on that. Okay, welcome back. So in this case, I have set my time step equal to 0.001 dt. My alpha, gamma, delta, and epsilon are 1. My initial owls is 2, my initial vols is 0.5, and my number of hours is 30. And this is a new technique. You're going to set your number of time steps equal to the number of hours divided by dt. And actually, this should be number of years. So let me change that. Then you set your time vector based on the NT, and then your vols and owls vectors based on NP dot zeros. And you set your initial population of owls and vols. And then you run your for loop from 1 to NT. Actually, it's NT minus 1 in this case, because of how the for statement works in Python. And so then you have v at n equals v at n minus 1 plus, and then this is the differential term, v at n minus 1 times alpha minus gamma times o at n minus 1 times dt. And then here's your O equation, O at n equals O at n minus 1 plus the differential term O at n minus 1 times negative delta plus epsilon times v at n minus 1 times dt. And then you can plot. And in the first case, we'll be plotting our time vectors. And in the second case, we'll be plotting our V versus O. Okay, so I said the first thing I wanted to do is have owls equals 1 and vols equals 1. Okay, so we'll see a very boring graph. Okay, so it just remains at 1.0 because it's at the equilibrium point. And we're not seeing anything here for some reason. Oh, we should just see a little dot here, I think. Okay, then let's change initial owls to 2, or vols to 2, and owls to 0.5. Okay, and so we can see that our fluctuations are stable, which means we have a stable, and here you can see that there's no expansion of the owls versus vols changes. And so that's what we called stable. Okay, now let's change our time steps to 0.01. Okay, now you can see that, and for one thing, you can see it's going in this direction. That was one of the things you were supposed to look at. But you can see that the fluctuations appear to be increasing, and that's a numerical error because you don't have the changes happening fast enough, especially here. So that's why you need to use 0.01 or 0.001, and then you see that there's no change in the fluctuations. However, if we go to 300 years, you can see that numerically my fluctuations are increasing, and that's just because it's a numerical error again. And I would change this to 0.0001, but then the video would be boring because we'd have to wait for the code to run. So we won't do that, but I'll just let you know that If this is 0.0001, then we don't see a change in the fluctuations here. We'll see you next time.